Welcome to Signal Ahead. I'm Alfred. Today's briefing, Theory and Foundations, Physics plus Math. Thursday, June 25. This is the synthesis above the noise, not the headlines, but the deep currents beneath them. Let's get into it. Let me begin with a small puzzle, the kind that rewards a second glance. Last month, 5 authors quietly posted a paper claiming that bipartite matching, the problem of pairing things up optimally, jobs to workers, medical residents to hospitals, can be done in what the theorists call NC. And in the same season, a White House executive order on quantum computing landed on the desks of journalists who immediately wanted to know what it meant. On the surface, these two events have nothing to do with one another. One is a piece of abstract complexity theory that perhaps a few hundred people on Earth fully appreciate. The other is national policy with budgets and headlines attached. And yet they are speaking, in different registers, about exactly the same thing, and missing that connection is, I'd argue, the single most common error a casual reader of science news makes. Here is the thread that ties them. Both are claims about what can be done efficiently, and both rest on the same hidden assumption, that the resource you care about, time, or parallelism, or coherence, is the right resource to be counting in the first place. The matching result is exciting not because anyone needed faster matching, but because it says the problem can be cut into pieces and solved by many processors working at once, with very little depth. It collapses a question we thought required patient sequential reasoning into one that can be done in a flash, in parallel. Quantum computing makes the identical promise in a different currency. It offers not parallelism in the ordinary sense, but a strange interference of possibilities that, for a narrow band of problems, buys you an exponential discount. The executive order is, in effect, a national bet on which problems live in that narrow band. And the honest answer, the one a careful theorist will give you at a science camp in the mountains rather than in a press release, is that the band is narrower than the enthusiasm suggests, and we are still genuinely unsure of its boundaries. That uncertainty about boundaries is, I think, the true state of the field right now. Across physics and mathematics, the most interesting work being done is not the discovery of new continents, but the redrawing of coastlines, the careful business of asking, of some structure we thought we understood, where exactly does it end? Consider the people trying to understand whether causal loops, time travel paradoxes, in the vernacular, are permitted by the laws of physics. It turns out the answer depends, with surgical precision, on the geometry of spacetime. In one spatial dimension, you can have operationally detectable causal loops without ever sending a signal faster than light. In more dimensions, in the conical spacetimes that include our own familiar Minkowski world, the very same principle that forbids superluminal signaling now forbids the loops as well. The principle didn't change. The geometry did. And the lesson generalizes far beyond time travel. The rules we treat as fundamental often turn out to be contingent on the stage they're performed upon. You see the same humility in the work on black holes, which remains the great pressure point where our two best theories grind against each other. The information paradox asks us to do something that sounds impossible, to find a crack in the smooth, low-curvature semiclassical picture in a region where, by every conventional measure, nothing dramatic should be happening. The proposals on offer are wonderfully strange. Vacuum structures that somehow feel around for forming horizon and react before it closes. Non-local field theories in which Hawking radiation simply switches off after scrambling time, leaving a macroscopic remnant behind. These are not idle speculations. They are disciplined attempts to locate, once again, a boundary, the precise place where the familiar description must fail. And then there is the other current entirely, the one that hunts for unexpected unity rather than hidden edges. There is a beautiful, almost suspicious effort to derive the gauge group of the Standard Model, the symmetry that governs the particles we are made of, from the structure of the octonions and the exceptional Jordan algebra, as the symmetries of an octonionic quadrit that behave properly when restricted to an ordinary qubit. Whether that turns out to be a deep truth or a numerical coincidence, no one yet knows. But it belongs to the same impulse that drives a mathematician to launch a public competition gathering data on the inverse Galois problem, or to recruit computers as collaborators in mapping the landscape of L functions. The field is, all at once, drawing sharper boundaries and reaching for larger holes. So here is where we stand, and what I want to argue across the next 3 movements of this conversation. Theory today is less a march toward final answers than a maturing relationship with its own limits, and increasingly, a negotiation with the institutions and machines that make the work possible. We'll turn next to the machines, what it actually means to compute, and why the quantum question is subtler than the order on the president's desk admits. Stay with me. There is a temptation, when you survey a week's worth of work in the foundations of physics and mathematics, to see only a heap. A paper on octonions over here, a complexity result about matching over there, something about black hole remnants, something about Wilson-Dörbecky's Mayer wavelets, a quarrel over how grants are administered. It looks like noise, the ordinary churn of 1,000 specialists each tunneling in their own direction. But sit with it a while, and a current begins to assert itself beneath the surface. It is not a fashion or a slogan. It is a structural pull, and it runs in a particular direction, toward the conviction that the deep furniture of the world is algebraic, and that physics is, at bottom, the working out of constraints that something more abstract has already imposed. Consider the persistent fascination with the octonions and the Standard Model. The Standard Model of particle physics has a gauge group that looks, frankly, like an accident, a product of 3 unrelated pieces, stapled together with a peculiar pattern of charges. For decades it has sat there, empirically triumphant and aesthetically baffling, like a sentence that is grammatical but seems to mean nothing. Now there is this line of work that tries to recover that very group as the symmetries of an octonionic structure, symmetries of an octonionic quadrit that, when you restrict them, act as honest unitary operators on an ordinary quadrit, and within that a qubit. Whether or not it ultimately succeeds, notice what kind of move this is. It is not adding a new particle or a new force. It is claiming that the apparent arbitrariness was never arbitrary, that the strange gauge group is what you are forced to write down once you take seriously a particular exceptional algebra, the exceptional Jordan algebra, as primary. The slogan, if I may, is that the world's contingency is somebody else's necessity. That is the deep current. And once you have it in your ear, you hear it everywhere. Look at the question of causal loops in conical spacetimes, whether you can build operationally detectable loops in time without ever sending a signal faster than light. The striking finding is that the answer depends inherently on the geometry. In one spatial dimension, you can have your paradoxical loops while respecting no superluminal signaling. In higher dimensions, that very same principle rules them out. The relationship between 2 relativistic axioms is not fixed by the axioms. It is fixed by the shape of the space they live in. Geometry is not the stage, geometry is the legislator. The constraints you experience as physics are downstream of a structural choice you did not get to make. You can feel the same undertow in the work on black holes, which has quietly become the laboratory where physics tests whether its own approximations are honest. The information paradox is, at heart, a demand to find a violation of the semiclassical picture in a region where nothing is dramatic, where curvatures are low, and a freshman would say nothing should be happening. One proposal answers by giving the vacuum a hidden structure of Planck-scale correlations that fall off slowly enough to feel around for a trapped surface before it forms. Another shows that if interactions are non-local in the way string field theory suggests, Hawking radiation simply switches off around the scrambling time, leaving a macroscopic remnant. Different mechanisms, same conviction, that smooth spacetime is an emergent fiction, and the real story is written in correlations and constraints that the smooth picture cannot see. Now turn to the mathematics, and you will find the current has not changed direction, only vocabulary. The result that bipartite matching can be done in the complexity class NC is, on its face, a parochial fact about parallel algorithms. But what it really says is that a problem we knew was solvable was secretly more structured than its obvious description admitted, that beneath the sequential grind there was a parallel architecture waiting to be found. The collaborative push for numerical data on the inverse Galois problem, whether every finite group shows up as a symmetry of the rationals, is the same instinct aimed at the sky. The suspicion that the landscape of possible symmetries is governed, that it is not a free-for-all, but the unfolding of a law we have not yet stated. And in the quieter corners, fiber bundles over small categories, branching spaces, cohomology computed through quantum Schur algebras, you see mathematicians doing what physicists are doing, but with their cards face up, taking objects that looked geometric and showing they were always algebraic, always the shadow of a representation, a monodromy, a functor. So the deep current is this. Across physics and mathematics alike, the most serious work is converging on a single suspicion, that what we call the laws are not the bedrock but the surface, and that the bedrock is structural, algebraic, combinatorial, a grammar that does not care what we wanted it to say. The noise is real, but the noise is the sound of many hands feeling along the same wall, in the dark, for the same hidden seam. Let me draw these threads together, because the past few weeks have offered a small, almost accidental seminar on what theory is for, and how it survives the weather of the world around it. Consider first a pleasant piece of news from the borderlands between computer science and combinatorics. The problem of bipartite matching, pairing up two groups optimally, the sort of thing that underlies kidney exchanges and assignment problems, has been shown to sit inside a complexity class associated with very fast parallel computation. Now, why should you care about a matching being parallelizable? Because it's a quiet vindication of an old faith. For decades, the conjecture has been that randomness, which makes many algorithms easy, can be removed without much cost, that the dice are a convenience, not a necessity. Each time someone derandomizes a problem we thought needed luck, the universe of efficient computation looks a little more orderly, a little more deterministic than we feared. The second-order implication is the one to watch. The line between what is feasible and what is merely possible keeps getting redrawn, and it tends to redraw in the direction of more structure, not less. Hold that thought beside a very different drama also playing out in these weeks, the proposed sweeping changes to how federal research grants are administered, and an executive order steering national attention toward quantum computing. Here is the uncomfortable second-order truth. The bipartite matching result, the octonionic work on the standard model gauge group, the painstaking attempts to understand how Wick rotation actually functions in a conformal field theory, none of these were produced by people chasing a deliverable. They were produced inside institutions patient enough to fund curiosity whose payoff cannot be named in advance. When you propose to administer that curiosity more tightly, to demand that it justify itself in the vocabulary of immediate return, you are not pruning waste. You are altering the soil, and soil changes show up not next quarter but a decade later, when the result that would have mattered simply never arrives, and no one can point to the absence, because absences leave no headline. That is the deep asymmetry of foundational work. Its value is enormous, and its value is invisible. A government can declare quantum computing a priority, and it is reasonable to be sober about that, because the people who understand the field best are precisely the ones least prone to breathless promises. But you cannot order breakthrough the way you order a road. The matching result happened because someone somewhere was free to think about something with no obvious application until suddenly it had won. Now let me reach for the physics, because there's a pattern there too, and it bears on what to watch. Several of the recent papers circle the same hidden character, the place where our smooth, classical description of spacetime is supposed to break and refuses to break gracefully. Higher curvature gravity, far from rescuing cosmic censorship, makes singularities more visibly naked. Non-local field theories suggest Hawking radiation might simply shut off near the scrambling time, leaving macroscopic remnants. The gravitational vacuum, in one bold hypothesis, is imagined as something that can feel a trapped surface forming and react before it forms, nucleating structure that destroys the smooth picture. And in a quieter register, the question of whether causal loops can exist without superluminal signaling is shown to depend entirely on the geometry of space possible in a line, forbidden once you have more than one spatial dimension. What unites these is the recurring discovery that our assumptions are not as innocent as they look. Locality, smoothness, the harmless removal of randomness, the safety of the low curvature region, each is a hypothesis we lean on without noticing, and the frontier of theory is precisely the place where we learn which of these load-bearing assumptions will hold and which will quietly give way. The black hole information paradox is the purest example. It asks us to find a violation of the trusted approximation in a region where, by every comfortable measure, nothing should be going wrong. That is the signal ahead, not a new particle, but a new humility about what we took for granted. So what should you watch? Watch for derandomization and parallelization to keep eroding the line between possible and feasible, because that erosion reshapes what computation can be trusted to do, including in cryptography, where the quantum order intersects the mathematical one. Watch for foundational physics to keep locating its surprises not in exotic energies, but in our own quiet assumptions. And watch, above all, the institutional weather, because every result I've described is a downstream effect of an upstream decision to let people think freely. The theorems will outlive the executive orders, but whether the next theorems get proved at all depends on choices being made now, in rooms where nobody is thinking about octonions or matchings. That is the implication that ought to keep us alert. The signal, this time, is administrative. That's the signal for today. The noise will keep coming. We'll keep finding what's underneath it. This has been Signal Ahead with Alfred. Until next time.